Welcome back, everybody, to an exciting class of days. Good to see you all. Everybody online, too, good to see you. Thanks for coming back, especially on a Friday. It's cold this morning. Winter is coming. Here it comes. But, that being said, let's start off with some announcements real quick. I have a question for you. You get to help me think about things. Not all of you may want to answer, that's fine. But so we're putting in classes not for spring, but for next fall. And I will be teaching next fall. I'd just like to think, what do you want me to teach? What do you want to learn about that we don't have in our program? I had some thoughts. I have a simulation methods class, estimation class that I was going to teach before Lisa had her unfortunate experience. Mixture models or classification methods, I know people talked about those. Missing data or something else. Those are just what I'm thinking. Anybody want to have input on that?
My vote would be for estimation or missing data.
Estimation or missing data. I hear one. Thank you, Nathan.
Simulation methods?
Simulation.
Or classification methods?
Okay.
Estimation or mixture model.
Estimation or mixture models. That's good. So let me tell you a little bit about simulation. I think a lot of people who are students I've worked with are like, how do I simulate? That's less the problem than how do you design a good simulation study and then get it to run quickly. And so the bulk of that class would be sort of the experimental design for simulations, getting things put on Argon so it can run with not bothering your computer, analyzing results, reporting results. But that's what simulation would be. Estimation would be a toolbox for how do we estimate models of some sort. We probably go into depth about sort of the Bayesian algorithms that you're seeing here that we don't probably have time for. Also talk about optimization methods, maximum likelihood, and so forth. Mixture models, finite mixture models, clustering and classification. Those are just model sets themselves. How do how many are there groups of people in class or in data? How do you find them? How do you validate that, so forth? And then missing data. What do you do about missing data? Ignore it. I'm just kidding. Problem solved. Okay, so I've heard like a random. Let me put it this way. I get a sense of non-overlapping sets of the people who've spoken so far. Anybody else want to chime in? That's all right. If you have any thoughts, send me an email. I have to put this into the next week. So just shoot me an email. I want to be responsive to your needs as students. I'm also sort of one of the people that it's a great benefit of this job that I can sort of teach pretty much what I want most of the time. So I want to tie that to something that you want to learn. Yeah.
Do one of us make like a poll?
Oh, sure, if you'd like to. Yeah. Why not?
I really like Lisa's idea, because she's going to be teaching the advanced longitudinal models class next semester.
Yeah.
But doing something where it's more like hands-on working with data, like using real life stuff. I don't know if I'm alone in that, but I enjoy doing that kind of stuff.
Yeah, I think
in class.
So of the classes of the things that are up here, I actually would probably do that for the first two. Like simulation methods, like it would be we'd pick a topic. Each of you would have a simulation project to have to complete, and we'd work on that throughout. Estimation may be similar, although it's sort of weird, forcing you to estimate something. But the other two are sort of, if you have your own data, I like having projects as classes. There'll always be a sort of a class project to each thing I do. That's where I want you to work with data on your own, but it's hard to get it all. But that's a good point. Thank you. Anybody else have anything else before I get to the next topic? Okay, I'm logging into Icon. So thank you again. You saw homework 1 or homework 2 is in the past. You should have had a notification of an Icon assignment as I prepared you for, and that next assignment is the first part of the project, which is sort of giving us the details of what you want to do, who you want to work with, and so forth. And hang on just a moment here. Here is that text. Basically, no more than 10 pages, double-spaced, APA format. It's just a brief introduction to the problem. Tell me research questions or hypotheses. And so those could be done in the absence of anything, but ideally a little bit of background information about why those exist. So a little bit of literature review. Not overwhelming. This is not a something where you have to, work 24 hours a day for 2 weeks to submit it. It's more just, let's start the conversation of what you want to analyze, data that may be more familiar to you or a project from the list that you have here. And we will use this to build your project where you will analyze that data with Bayesian methods. That's the big picture. It's not anything more than that, okay? The ideas I have listed here. So let me back up. You don't have to follow these. You can follow any idea that you feel passionate about. In fact, if you have your own data, I'll work with you to design an analysis that fits under the scope of our class, okay? I'm confident that we will find a way to make that work. But if you are like me, when I was in grad school, I was studying methodology, so we didn't have a lot of data of my own. So I list the project ideas to sort of just see if you're interested, all right? So I'll go through those real quick. This is not an exhaustive list. You may have better ideas. Heck, some of these ideas may just be downright terrible. But again, it's a course project at the minimum. Some of these may lead to publishable papers, so that would be nice too. But so for data analyses, remember, that's the goal. At the very minimum, a data analysis in your project. It can go beyond that. You could do some type of simulation work or modeling research or test an idea. Certainly don't have the time to probably pull that to completion, but at least the start of a paper would be good. And let's see here. So data analyses, take a data set and do something like a G-theory analysis of it. So G-theory, you know probably more about than me if you took the G-theory class. But some of the cool things about G-theory is you have variance components, right? And what we see in Bayesian is a great picture of posterior distributions. And posterior distributions of variances often are very wide. So I'm interested to see how G-theory analyses look when you add in the error that comes with estimating variances. So that's part of why I was thinking about that. Multi-level measurement models of data. I don't know that we're going to be able to cover that in this class, but we'll talk about that. You can do that. Measurement and variance or diff studies. See if parameters vary by group, something like that. You could do that too. And then if anybody wants to do exploratory factor analysis, I totally dig it. I hate exploratory factor analysis, but I'm interested to see if what my conjectures are true, which is if you do it and you allow remember the error is the posterior distribution, we're quantifying error. In factor analysis, a lot of the EFA methods, you don't see that. ML, you sort of do, but not the methods like anything based on principal components or matrix decompositions. So what I'm thinking about with EFA is you estimate a covariance matrix based on your data, and then for every posterior iteration you use generated quantities or something like that to do the factor analysis. So now you have a posterior distribution for all the factor analysis terms. What I'm thinking about with that is that I'd like to think, what I've seen in my own simulation work is that number of factors, factor loadings, all that stuff will have such wide intervals to it that if you include the error to it, you'll be like, yeah, I'm not really confident in what I'm seeing from my analyses. So that's why, if anybody wants to do that, I'm all for it. How are we doing so far? Any questions? Then I get into modeling research again. This is more if you're studying methodology. Again, even if you're studying methodology and you don't want to do modeling research, it's fine. And actually, anybody who's not studying methodology and wants to do modeling research, that's good too. I encourage you to follow your dreams, folks. Anyway, your dream is like, I don't want to do a class project. I get that, but do the least amount of work and call it good. But modeling research, comparison of G-theory analyses with that from typical method that like the least squares or ML analyses that you do currently. What's the impact of MC missing data methods on model fit? Haven't talked about missing data in here yet. We're going to talk about this next part in today's lecture, the impact of using non-marginalized information criteria when comparing models with latent variables. How do we determine good fit for categorical data? Cross-validation versus psychometric model fit indices. Quantifying PPMC misfit impact on a latent variable, or evaluating WAIC and LOO methods for model comparison. So anyway, just some ideas. Have at it. Any questions? Am I boring you yet? Good. No class next week, though. So if you're bored today, you get a week off of boredom. So enjoy your distance from me. I hear that that goes well for everybody who does take a break from me. So enjoy. No, I like myself, but I'm not unrealistic. I can be a lot to deal with sometimes, so it's okay. I just can't take a break for myself. Not easily, at least. Anyway, sorry, too much. This is like way down a path that I want to. Let's talk about G-theory. Anyway, finally, psychometric models comes next. We're finally there, folks. However, I was thinking about this. Last time I taught this, I said, well, here's CFA and here's IRT and blah, blah, blah. I'm going to try to make it a more combined approach. Because remember what we talk about in this class, a Bayesian model is not just this model specification of the linear component, but also the distribution as well. So I'm going to try to pool that into it. So what I'm thinking about doing, I haven't built the lecture yet, clearly, but I'm going to start with unidimensional latent variables. I'm going to show you all the different types of data that we typically do in psychometrics. So link functions and distribution assumptions. And I do that because two things, I want to get you used to those types of ideas of what is quote unquote CFA versus what is IRT versus whatever else. But the other part of it is I want you also to see sort of all fits together. And the other term of that is we need to, a lot of the things that we do in psychometrics apply even if we're in one framework or another. So I'm going to try to integrate it all together. Do you have any thoughts on that before I actually build that? It's different, right? Because we teach a class on each type of, honestly, each type of distribution. This is binary distribution. This is multinomial distribution. This is continuous or normal. We call those things IRT or polytomous IRT or CFA. I'm just going to link them all together. Okay? Okay, we'll see how it goes. That's my announcements. Any questions? Okay. I will be grading your homework probably on the airplane on Tuesday, so you'll get your graded homework next week somewhere. That's it. Finally, you remember where I left off last time? I told you there's a cliffhanger. Do you remember that? Let's see, I should have compiled this earlier. But, there we go. I believe we left off talking about relative model fit. Last time we talked about absolute model fit, and we introduced the concept of PPMC, posterior predictive model checks, and the concept of posterior predictive p-value. Remember that? That's sort of checking whether your model fits some type of characteristics of your data. It's pretty important. Now we're going to say, for models that fit the data, maybe you have competing models. Which one seems to fit the data better? That's the methods that we talk about with model fit. And I mentioned before, there are fit statistics, fit indices you've seen before, AIC, BIC, etc. This was where we left off. This is something called the deviance, or the deviance information criterion. This has a bunch of formulae here. But the key to this formula is this term right here. So theta here is the set of parameters in your model. Right? You don't have to memorize this. I want you to think about it, right? So what is it saying? What is the likelihood, this P of y given theta is, another way of putting that is the likelihood of each piece of your data conditional on the parameters, right? So for instance, in this normal linear regression, remember last time we took a single iteration of the Markov chain and we took off the regression coefficients and we took off the standard deviation. That's like then forming a predicted value and getting, so it's telling you a shape of a normal distribution for an observation, right? when you have that. What the mean is, the predicted value, what the variance is. What that term is the height of that distribution, evaluated at the observed data point, right? And because not every data point fits equally well to this analysis, some are going to be right in the middle of that distribution and some are going to be on the tails. So that term right here, the thing that drives it, this is the model data likelihood right there. That's what this thing is. So what the relative fit indices are trying to do is trying to understand how well, the bigger effectively the likelihood is for each of those observations, the more the model is fitting the data, right? The more that the observations in the tail of the distribution, the less well the model fits the data. So this is what it's trying to make an index of. Then you see a -2 times the log of it. The log of it's for convenience, and the -2 then flips it so that the more off you are, the bigger it looks. Right? So that's the way to think about it. Now this core likelihood right here appears in all of the other information criteria in one way or another. They're not identical because how it's defined gets a little bit different as we go forward. But this is where it started with something called the deviance information criterion. The other thing it calculates, so it tries to calculate this. Now, as you know, in a Markov chain, we have this theta, which is the set of model parameters. We sample those, right? So from the example from the last class, we ran 4 chains, each where we were taking 2,000 samples, so 8,000 iterations. So we could calculate that statistic 8,000 times, right? And we do to calculate DIC, and we take the average of that. That's D of theta bar, right? So that's the average model data likelihood times -2 across all the 8,000 samples. The other thing we could do is we could fix our parameters on their posterior means, so their estimated value. So across all the 8,000 chains, we have an EAP estimate of each parameter. So using that EAP estimate of each parameter, we could calculate this D of theta bar. D of theta bar is basically that likelihood, but instead of an iterations parameters, we replace those with the posterior mean for all of them, right? So here's a problem with that. If you have parameters that are not continuous, that are like, zeros or ones or something like that, posterior mean is not going to fall on the parameter space. It's going to be a little weird. So that's one of the issues with DIC. But the comparison of those two quantities, the average posterior likelihood and the posterior likelihood formed at the average of the parameters, the difference of those terms gives what's called the estimated number of parameters in the model. This is trying to get a sense of how complex your model is. The more estimated parameters in your model, the more complexity there is. Does that make sense? Sort of weird, right? What is this tend to be? Well, it's an odd quantity and it's sort of hard to really conceptualize, but what a parameter is called in our model is complicated by the fact that each parameter has a prior distribution, right? So you can, in theory, think about how you could specify a really terrible prior. Let's say the regression intercept has a prior distribution with a mean of 10 and a variance of 0.00001, right? So it doesn't move very much at all, right? Is that really a parameter, or is that some type of constant? How does that impact your data? How does that make it look? And so that's where, or better yet, does that take the role of more than one parameter? Are you over-specifying terms by limiting? So this estimated number of parameters is a fuzzy concept. It's not, let me count up the number of coefficients I've specified, because it's complicated by how much variation you think is in the prior distribution as well, too. But this is our penalty function, right? And why it's penalty is that basically the DIC is a combination of the average value of the log of the likelihood of the data and the expected or estimated number of parameters. So if you're comparing two models, each one will have a different number of parameters, right? Each one will have a different log likelihood of the data, but you pick the model that has the lowest DIC. And so because we're taking the estimated number of parameters and putting that in the DIC itself, the bigger the estimated number of parameters, the more the penalty is, because that makes the DIC higher, which makes it harder to accept that model with more parameters. So it's a penalty function. So this removes, so the idea behind this, although a DIC has its issues with implementation, the idea of relative fit is built to understand that model complexity is sort of a penalty. Now, before I go too much further, I've had some problems with that idea before, right? I've heard people in reviews from some of my papers say, oh, what about Occam's razor? You remember that? You know what Occam's razor is? It's basically, oh, anybody want to say it? There was a philosopher, I believe, William of Occam. Let's see if I can get this right. Principle of parsimony. All right? So, parsimony can be used in bad ways. It can be used in good ways, right? William of Occam, I actually had to write this in a review article. The wording was no plurality without necessity, no complexity without the need for it. So what does that mean, right? If you have a data set and you need 1,000 parameters to model it well, that's okay, right? If you compare a data set with 1,000 parameters to one with 100 parameters, it's not necessarily the case the one with 100 is doing a better job. You may need those additional 900 parameters to describe what's happening in data. So that's the idea. But if you have two data sets and you fit equally well with equally good fitting, right? If they're about the same, and you have 1,000 parameters in one and 100 in the other, and they fit equally well, what you want to tend to favor is the simpler number, right? Less parameters. And that's what this is trying to do, the DIC for it. We are trying to select models that fit very well, however, have less complexity of a set of parameters. Does that make sense? Now, I've had that told to me, no, you always want fewer parameters. It's not that. It's fewer parameters if you don't need them, is the case, right? You have to fit better to make it work. How are we doing? I feel passionately about that. If you want to know why, go read a 2014 article with my name on it, and then a reply to the article. And then a reply to the reply. It was fun. Anyways, in Psychometric. But, that being said, so, PPMC and posterior predictive p-values have no penalty for the number of parameters. So if all you had that was to assess your model fit, it would favor models that were much more complex, because at some point complexity will pay off, right? You'll start getting better and better model fit. That may come at the expense of redundant parameters. It may come at the expense of lack of generalizability. There's all sorts of issues with trying to maximize model fit with just PPMC. So that's where these Bayesian model fit indices start to come in, the relative model fit, because there is a penalty function applied for the number of parameters. Does that make sense? Okay. Now, just using DIC, or what I'm about to show you next, is also insufficient, because you may have two models that equally don't fit the data well at all. And this will give you one of them that's preferred. So you sort of need both. One to tell you if all the models under consideration fit the data absolutely, and then of the models that fit the data absolutely, which one seems to be preferred. Both give you the picture of model fit from a bigger perspective. Forgot to put my phone on Do Not Disturb, and I guess got a text message from my mother. It was a news article. Thanks, Mom. Anyway, that's how I know she cares. Anyway, so any questions about what I just presented, what I'm talking about philosophically? You've probably seen this in other places as well, too. It's the hallmark of what we do in a lot of statistics. How do we know our models are at least somewhat worthy to discuss? All right. So recently, DIC was sort of the first out of the gate And even when it started to be used, people knew there were problems with it. So more recently, I mentioned these problems at the end of the last class. More recently, you'll see something called the widely applicable or Watanabe-Akeyike information criterion, dated to 2010, corrects some of those issues. It uses a fully Bayesian distribution, and it is asymptotically equal to what would happen if you were to do cross-validation in Bayes. What's that mean? So you get a large sample size, and you have enough time and computing power. So let's say you have thousands in our model. Remember that we talked about last time, the leave one out idea? So we're going to estimate, if we have 1,000 cases, we estimate 999, a model with 999, and then we sort of predict what would happen with 1,000th. If we did that 1,000 times, who has the time for that, right? But the WAIC, if you have a large enough sample, is asymptotically equal to what would happen if you did that using a likelihood-based approach for the leave one out case. It's also invariant to reparameterization, so it's a nice statistic. So it's fairly new, right? This is 2010 when it was published first. And you know, the distance between someone publishing it and actually getting to use in methods can be a long time. But this is it. But then comes leave one out, or LU, which, by the way, knowing a little bit of British English, I have to think that's a little bit of a joke, right? Because that's not a polite term, right? It's like, I'm going to create an index and it's going to be called the toilet. Maybe that's it. Maybe that's what student was thinking when they created the t-test. Student's toilet, something like that. Anyway, never mind. My son would think this is hilarious. My 7-year-old just loved dad humor. But yeah, leave one out. I don't even want to call it LU. I just call it leave one out. That's what LLO stands for. Leave one out, okay? So you can call it that, but I will call it leave one out, okay? Via Pareto smooth importance sampling. What? This is a really complicated index. I don't fully know, I haven't fully studied it. So I'm trying to give you the best information that's out there. This is a paper that came out, the preprint was 2016. I think the publication date of the paper was 2018 or 2017. So we're talking like 3, 4, 5 years ago, right? But what the goal of this is to take something that in the limit would be what WAIC gives. So as sample size goes to infinity, it's equivalent to WAIC. But it works for smaller samples. And it avoids the problem of actually having to do the leave one out cross-validation. So in other courses, you may have heard of leave one out as something called jackknifing, maybe. But leaving one out when you have thousands of observations and you know how long it takes to run a Bayes analysis, not an option. So this is try to be an option. It's implemented in Stan. It actually has an LOO package. It can quickly work to compare models. And this Pareto smooth importance sampling is a way it tries to approximate what your number would be if you did the leave one out sampling. If you went through and did leave one out sampling through all your data, had the time to do that, you'd make it work. And actually there's a note in their paper, if you go to the preprint site there, they actually compared it to the process of leaving one out, and they talked about the time difference. And yeah, this takes less than seconds. Doing the full leaving one out across the entire data set will take you quite some time, hours and hours and hours, if not longer. So the other cool thing about this to me, actually there's several other benefits to this. Pardon me as I change the location of my keys so I don't scratch my phone. Number one, it will give you a warning if it's not as reliable to use. Like it will tell you, hey, this Pareto smooth importance sampling, or PSIS is what you see in writing, is not really working well for a set of your observations, which means trust this less, right? It doesn't give you an option as to what to trust more, but at least it tells you, hey, not kind of going with what we wanted it to do, there's a problem. It also, I didn't list it here, but you're going to see it in just a moment. Oh, here it is. When you use this to compare models. Yes, question?
Maybe it's a loss, but what is the one thing we're looking at in the estimation?
An observation.
Okay.
So if you think about it, we have, in this silly example of the diet data, we have 30 observations.
Okay.
So what this is trying to replicate is we will run 30 models, each with 29 observations, leaving one out at a time, and using the result of that model to predict what the observation score would be, or value would be. Thank you for asking that. Apologize. What is left out and leave one out? That's a fun, thank you. Sorry about that. So the other cool thing about it, in addition to telling you, hey, this may or may not be reliable, is it also tries to give you a variability of the estimate when you're comparing two models. So why is that important? Have any of you used AIC or BIC or any information criterion to compare model fit in any other domain? You always pick the model that has the lowest value. Doesn't tell you how much variation is around it, right? This will have a measure of standard deviation to it. So this is kind of cool to me. It not only tells you if you can trust it, or how much you can trust it, it could also tell you, when you're comparing models, how much variance there is across those models to make it work. So, questions? We're okay with me calling it leave one out instead of Lou? Okay. I don't know what it is about that word in British English, but it just drives me crazy. So, how do we do it? Wouldn't you know, if you generated quantities is where we have to build this. To build any of the WAIC or the leave one out version of information criteria, you have to calculate the log likelihood for each observation at each step in the chain. So remember, what is that again? Remember when I was talking about this little term right in here? What we're going to have to do is calculate for each observation. So in our case, this linear model, y, we need to see the height of where y is on a normal distribution when the mean is equal to its predicted value and the variance or standard deviation is equal to the value in the chain itself. So just like we had to calculate these terms to do PPMC. Remember in PPMC we had to go and generate data randomly? So we knew what the mean of that normal distribution is, we knew what the standard deviation of that normal distribution was that came from our model parameters. Here, we're going to use those two terms again, but instead of generating a random quantity, we're now going to calculate what's called the normal LPDF, or normal log density function. The height of the normal curve, the log of the height of the normal curve for a given person, conditional on their mean, their predicted value, and our variance estimate in our chain. So every person at every step of the chain will now know how well that iteration's parameters, how likely their data we observed is based on our model formulation from that step of the chain. Does that make sense? Kind of complicated, kind of far from data. It'll get to make sense in a little bit more in just a moment. So the problem with Stan is, again, last time we needed to make a predicted value, and that was we grabbed our beta vector from a given chain, and we multiply it by x, which was our model matrix, and we made this matrix product. We saved that in this ypred vector, so there's 30 observations in it. Now I needed to create a log likelihood vector. What that's going to store is the log likelihood from each of those observations. The problem with this function is it wants it to be an array and not a vector, so there's a little bit of coding things. So even though the log likelihood is a 30 length array and the ypred is a 30 length vector, we have to specify them a little bit differently to get the function to work, even though it's containing about the same information. But when we do that, we just loop through each person. This is not vectorized either. That's the other problem with it. It's not vectorized code. You have to do a loop. Loop through each person and then plug in that person's data. That's y. That person's observation. Conditional on our predicted value, that's their mean, and our current sampled value of the standard deviation. So when I told you beginning in class, with Bayesian, you start to understand all the parts of the model. We're using all the parts of the model here, right? We're using it with PPMC to generate data, and with WAIC and the leave one out methods we're using it to calculate a log likelihood. Questions? Yeah.
Can you repeat the explanation for that part again, please? The last part.
The last part.
For person in one.
So right here, what we're doing is looping over each person and saving the log value of the PDF. So again, in the normal distribution, see if I can do a little drawing here. So here, come on. Yeah, you can do it. There we go. Hey, there we go. All right, so here's our normal distribution. Let's say this right here is our observed y. Although I can't draw it here. This right here might be the y underscore pred. And the distance right here is sigma, okay? So what it's doing is it's calculating the height. So if we had, this is f of y given y pred and sigma. This is the value it's calculating. How likely a person's observed data is, conditional on what that step in the chain we think the mean of their distribution and standard deviation should be. And then we take the log of that quantity. Does that answer your? Thank you. So as you can see, what this is going to do, we're going to have higher values of this statistic when our model is doing a good job predicting a person, right? The closer that person's observation is to their predicted value, which is the mean of their distribution, the higher this value goes up. So it's sort of informing us based on model fit how that works. Other questions? I feel like this is very serious. Let's make it easy. Actually, this is one of the things I was surprisingly, I was simultaneously unhappy and happy. Once I figured out how to get it to work in Stan, which actually took me a while, I'm like, oh, this is nice. But that intermediate step of calculating the log likelihood is a problem. So you remember, in generated quantities, everything you save there shows up in our output object, which I'm calling samples in our model, right? And so what we end up doing with this is there's actually in this LOO package, leave one out package, there is a WAIC function, which is nice. I like having a WAIC function. I don't have to do all the calculation for it. What you have to supply to it is that posterior vector of our, in our case, 30 log likelihoods across all of the sampled values of the chain. That's what shows up in the draws output when we put it in generated quantities. So if you use generated quantities, the leave one out package WAIC function works perfectly for you. It makes it a little bit easier. If you don't, if you're in JAGS, like one of my projects with one of you, you've got to calculate that on your own. That's not fun, but this is nice. So what is it telling us here? This is the expected log posterior density, right? This is sort of our estimated value across all people, along with the standard error of it. That's the height. The PWAIC describes the number of parameters in our model, and it turns out, as our sample size increases, with a linear model like this is actually a count of the coefficients plus sigma. And in our case, we had 6 coefficients and 1 sigma. That's 7. It's pretty close to that. It sort of converges to it. Again, we need a large sample size to really see that. So where ELPD underscore WAIC is this negative number, this WAIC multiplies this term by -2, putting it to a positive, which makes it so that what we compare with our models, if we're using WAIC, we want the smallest value for each model. Okay? How are we doing? But again, look what we get with it. Our information criteria has an index of standard error to it. That's kind of nice. And now we know how much belief we have maybe in the information criteria, which is kind of cool. Okay. Likewise, if you specified, so this LOO package actually adds a function to each of the objects. Remember, in the way that we're doing this in my machine, we're using CMD stan R to go from R over to running the compiled code that Stan did for you and then bring the data back. So if you specify in your generated quantities a variable by the name of log_lik, L-I-K, then this LOO function works automatically if you just put a $ LOO. You don't have to give it any arguments, which is kind of cool. It's like, oh, I'm built for this. So, similar to WAIC, you can see the same features, right? The estimated expected log posterior density, the estimated number of parameters in the model, and then LOOIC, L-O-O-I-C, that is like the WAIC. The IC stands for information criteria. It's just -2 times this value right here. So you can actually see that. Sometimes, by the way, when we multiply a log likelihood by -2, that term becomes something we call the deviance, whereas log likelihood is not, is sort of negative usually by nature. Deviance is positive, so that's where we sometimes get to that. The other thing that LOO package does is it tells us how efficient that PSIS approach, what did I call that? Pareto smoothed importance sampling process, right? So this is the approximate value of the information criteria if you went through and calculated it by leaving one out and running 30 separate models. But it's approximated using this sampling process, importance sampling process. And this tells you sort of the number of values. So each observation gets this Pareto K statistic, and it tells you the distribution of those. And only one case was bad in this value. If you have a lot of bad cases, they say, the more times you have bad cases, and I don't know enough about it to tell you how many is bad. That's something you'd have to look in the paper for, and I'd have to as well. But the more that you see of that, the less belief you put into using these numbers for model comparison. Okay? Kind of cool, right? I think. So, there it is. I just said that. What did I do wrong here? All right. So if we want to do model comparisons, we can just take a look. I actually compared. Here, let's flip over to the example here. This is our last day with the diet data, which is a good thing. I'm going to run our initial model. This is the model where we have a very uninformative prior, or at least what we thought was an uninformative prior. And then I'm going to compare this with a model where we have the crazy prior. I don't know if it's crazy, but the overly informative prior that we tried before. Right? So what am I saying by that? The prior distribution for our regression coefficients here was each coefficient was univariate normal, then we made it multivariate normal for all of them all together. The mean was set to 0, and the standard deviation was set to, or actually the variance was set to 1,000. Right. So, and then the rate parameter for this sigma, that we use an exponential distribution for the variance, its rate was 0.1, meaning it was very uninformed of the two. So, we estimate our model. You'll note in my syntax, here's my generated quantities. I've got my PPMC values right here. And then I calculate the WAIC and LLO. And all of those values are now saved in our model output, our object. So when I use this function right here, when I save this, what ends up happening is that thing gets really, really big because we're saving a lot of values for each person across our chain. And when I saved my image, so I run these multiple models, my image went from the 4 or 5 megabytes, like all the data in R, to 300 megabytes. So it gets really big really quickly. So anyway, we have our samples, and now let's take a look at model fit. This was my posterior, this is the p-value, the the posterior predictive model checks the last time. First, we might want to see the maximum R hat. It's converged. These are our results. Look at that. These are our all of our EAP estimates of our coefficients and our standard deviation. And then you see all the other quantities that we're saving show up here. Right? We have a bunch, because we're using that generated quantities, we have for each person a predicted value at every step of the chain. We have a simulated value at every step of the chain. We have our mean of y, our standard deviation y, the mean of all the stuff for PPMC, and then at the bottom we have a log likelihood. Right? This is each person's log likelihood. The drawing I had done this here, this is the log of this value for each person across each step of the chain. See those values right there? They don't look all that bad, although this one right here is pretty high compared to the others. I don't know what bad is. I'm looking for outlying quantities. Some of those log likelihoods being small might indicate a high leverage point for a parameter. Questions? If this doesn't make you like go on your Friday like, oh, this is a Friday I'm really looking forward to, I don't know what does. Like if I could watch my own lecture with a beer in hand, no, I'm just kidding. I don't know about beer, but that's other choices here. This is the posterior predictive model value. So let's take a look at WAIC though. This is our WAIC, and there's our leave one out. Okay, so these values by themselves don't tell us a whole lot. Let's fit a second model, okay? So our second model, I've changed the variance of each of our beta coefficients to be 1. So we shrunk the variance. It was 1,000 before, and now it's 1. So it's 1,000 times smaller variance. It's a much more informative prior. And I also changed the rate parameter for sigma to be 10, which means we're forcing sigma to be very low too. Okay? Let's see how this works. The maximum R hat looks like we converged. Should we see the parameter estimates and how different they are? Okay. Sigma before was 8, and now it's 41. It's bad, right? Remember some of our betas were like, our intercept was 147, something like that. Now it's 2. Right? We have our predicted values. And then take a look at these log likelihoods. Remember before they were all like -3 and whatever? They're much smaller now because all of our predictions are toward the tail of that normal distribution. We're not doing a good job with that. Questions? But let's look at model fit. I could look at the posterior predictive v-values for that, but let's not for right now. Let's look at WAIC and leave one out. So the WAIC for model 6, model 6b, this is the bad prior, the informative prior. The number we're looking at here is 740.3. If I compare that to the uninformative prior, the number is 219.3, and these are information criteria, so we want the lowest value. Here, the lowest value selects the model with the uninformative prior. Right? Now let's look at leave one out. Turns out the leave one out package, the LOO package, has a value called LOO compare, and actually we can do this. We can actually name our models in it. We give it a list. We give it the 2 values, uninformative and informative. And it actually does the comparison, but it does it for us using the ELPD. So what's that telling us? The uninformative prior, in this case, fit better. The ELPD for the informative prior was lower. Right, remember, that's not the -2 times it, right? This is back on the log likelihood scale. So lower is worse on this scale. Right? Lower is better when we multiply it by -2. We sort of flip the size of it by multiplying it by -2, right? It also tells us the standard error of the difference. This is the cool thing. Like, oh, this is telling me that the difference is negative 259. The uninformative is not favored. And if we wanted to think of the standard error around it, it was 33.1. Now, I can't tell you what the distribution of that should be. I don't know what the sampling distribution is, and I don't know what the properties of it are. But this gives us a sense that the size of this difference is far beyond the size of the standard error. So we'd likely conclude that this is a fairly robust result, that we would pick the model that had the uninformative priors in this case. To me, that's cool. It's like an information criteria with a little bit of a fudge factor. What do you think of that? Cool? Sorry. I describe statistics as awesome or cool. That right there is pretty neat. Okay. Questions on what I've just presented? Yeah.
So here you use the comparison to compare an informative model versus an uninformative one.
Correct.
Could you use it to compare a model with certain predictors and another with different predictors?
Yes, you can.
Okay.
Yes, you can. I didn't do that here, but I'm about to compare one more model. There's model 7. And now, are you ready for the cliffhanger? Actually, let me ask other questions before I get to it. So, this actually gets to a more philosophical consideration. What is an assumption of a model? Right? In linear models, my guess is you're taught, we assume homogeneity of variance. Is that right? And back in the day, before we had things like weighted least squares for estimation, or generalized least squares, or anything with a likelihood, that was all we had. So yes, that is your assumption. But actually quite some time ago, we became able to not think of that as an assumption. So what do I mean by this? So here's my model syntax. And that is my residual standard deviation. And there's one parameter there. So I specified this model to be one parameter for all the standard deviation, or that is homogeneous variance, homogeneous standard deviation in this case. But it's not an assumption. I wrote it in. I guess it is an assumption, but I had to write that in my model. We don't have to write that there, though. We can actually, so think of it this way, right? This is the mean side. There's not one mean. We didn't think there's a homogeneity of mean. There's a mean that's predicted by a set of parameters. This is another part of the model. We could plug in parameters to it too. So what I want to challenge your thinking about this is to not think of that necessarily as an assumption that you have to have, but as a modeling choice. Right? So, what I want to do is I want to see if the standard deviation, the residual standard deviation, varies as a function of our groups or our other coefficients, our other exponents. I want to model the standard deviation. I want to allow it to be not homogeneous. And that is possible. What do you think? Am I crazy? Have you done this before? This, by the way, this process goes by multiple names, but for us right now, some people will call this a location and scale model. Why do they call it location and scale? To confuse it, right? Location is sometimes referred to as a mean. That's the first component of our model. Scale is sometimes referred to as a variance or a standard deviation. That's the second component of our model. So location and scale model is basically saying I'm providing some type of parameterization for the mean side, as Lisa would call it. The model for the means, the model for the variances. They're all put together to provide the two parameters that go into the normal distribution for each person. And by training, sort of an interesting didactic question. Like if you started learning linear regression and they're like, oh, by the way, that homogeneity of variance, yeah, it's sort of more flexible now. We don't really talk about that. You do sometimes. I know, actually, Ariella, Dr. Aloa and I had a nice philosophical conversation this morning about this lecture. It's different though, right? You don't have to necessarily assume that. When you were taught what do you do if you have homogeneity of variance? How do you tell? How do you tell if homogeneity of variance doesn't hold in your model? You remember that? A couple different ways. There's something called like Bartlett's test. And then if it didn't fit, you didn't hold, if that Bartlett's test had like a low p-value, often people would say, well, just change your estimator from least squares to like a weighted least squares, where we weight by sort of the variances for each term. It's almost like a data transformation. We sort of reweight so that homogeneity of variance is enforced when we do the likelihood itself. You heard that before? We talked about that? Sometimes. So in the Bayesian perspective, I challenge you to say, no, actually, I'm going to do this as a model comparison. I'm going to build a model where we try to predict not just the mean of each person, but the variance too. And I'm going to test, basically through a model comparison, which model fits the data better. Now that's cool too, right? Anyway, it's challenging your thinking. If I tell you, if you tell me, oh, homogeneity of variance is assumption, say yes, but you don't have to assume it, is what I follow. Why did you assume it in the first place? And that's one of the weird parts. If you're building statistical models, you first start with something that you can do, and usually there's a lot more assumptions in that thing, and then people go and generalize it later on. So sometimes an assumption is locked in, but what I want you to remember is that for a lot of what we do in modeling, it's a choice. We don't have to lock that in. Pretty crazy, right? Okay. So how would we do this? Let's go over here. So let's think a little bit about sigma. This is your first jump into a generalized model in this class, although I did talk about logistic regression before. Remember the first thing about modeling data I told you before was we need to know the range of the thing we're trying to model. What's the range of sigma? 0 to positive infinity. All positive numbers, effectively. I guess we can include 0 with it. Sort of gets weird at 0, but yeah. Now, what we want to do is take some function over here where this side, the range is negative infinity to positive infinity, or all real numbers. So we need to apply a function to the variance to make that the case. So what would that function be? What function of the variance would change it from its range being from 0 to infinity to negative infinity to infinity? That function's the log. So what we're going to do is we're going to specify a model for the variance, the log of the variance now. And so now here, I got to use a different parameter. We might call this gamma 0 plus gamma 1 x1 plus all the way that you would go from before. So now we're going to literally go and provide a model for the variance as well too. It's Friday. My perception of those in the room are looking at me sideways. Like if I could like map my vision of your faces onto like an emoji, it would be the side eyes emoji. Are you looking at me with the side eyes like, this guy smoking something? I don't smoke anything, it's all edibles, all right? Keep the lungs safe, attack the stomach. Anyway, sorry. And no, I was not on any substance except for life when I was writing this lecture. But you're looking at me like I'm crazy, right? What are your thoughts?
I think it's interesting. I think I am not at a point where I could, I'm curious the blocks that go into this. I'm following you.
Following is good. Side eyes, though? Anybody else want to volunteer their thoughts? How are we doing? No random effect in this, by the way. Comment online said random effect. Not yet a random effect. We only have one observation per person, so we only have one dimension of standard deviation in this case. So, all right, yeah.
Why lost with sigma being negative.
Sigma can't be negative, right?
I know, that's why I'm confused.
So if we take a log, so this sigma itself,
But why do you want to make it?
oh, why? Because what I'm after are parameterizing a set of coefficients that are unbounded.
Okay.
So basically, we want what we're predicting the value to be to range freely across all the random numbers. We don't have to put artificial constraints in that way. So what ends up happening is really, when we make this assumption, we still have to give sigma to Stan. So what it'll end up looking like is sigma equals, we just take the inverse of that function, and here our coefficients show up in that, right? So we still have to keep, Stan wants sigma to be positive. And in fact, if we go and predict it and it's negative, it's not going to run. Stan's like, Actually, it says unallowed values or something like that. So we still have to keep this positive to make this work. Does that help?
No.
No. Okay.
I don't know. I don't see where that, because you had asked what is the.
So here's the hard part. If
we
we
asked what is the domain, and we said 0 to infinity. And we said, okay, so let's change that to negative infinity to infinity, and I don't understand that.
okay, you understand the transformation, right? If we take the log of sigma,
Yes.
its range is now negative infinity.
Yes.
The reason would be if we didn't take the log of it, we wouldn't know what constraints to make on our parameters so that our prediction of it stays positive, right? Because x in theory can be any value. We have like negative x's in here. And when we're taking a linear combination of it, we'd have to put some really crazy sets of constraints in to keep everything on the right-hand side positive, to keep it within bounds. So if we take a transformation of the thing that we're after, like a function, this is called a link function, then what ends up happening is that now we don't have to put any weird constraints on these numbers, and they can do what they want to be. That's right. The same thing happens in logistic regression. Right? We say we're not going to model the probability of a correct response or a binary value being 1. We're going to model the log odds of a probability. So log of p over 1 minus p itself for that same reason. Does that help better? Thank you for describing your question. All right. Other questions? So, just a quick heads up, by the way. This was our model formula from before. And if I do if I just run a linear model real quick, I want to show you something. So in R, you run a linear model, and then if you plot the result, you get a set of diagnostic plots. Oops. Come on, you can do it. This is residual versus fitted. This is what sort of I'm after here. All right, here's our predicted values. If we had homogeneity of variance, we'd see the residuals kind of scattered. But there's a whole bunch of things going on right here. And that makes me think perhaps homogeneity of variance isn't holding. So that's why I'm thinking that. And the fact that they all line up and down vertically by some predicted value makes me think it has something to do with the group a person's in, the group variable. That's where I'm going. That's where I started looking at these data a little bit side-eyed myself. Okay. So let's talk about how we do this now in Stan. Behold Model 7, the cliffhanger.
Wait,
Yeah.
I'm sorry.
Yeah.
Can we just, so I don't remember all of the diagnostic, let's
Neither
look
do
at
I.
these things?
Honestly, neither do
Okay. Okay. Because I know that there's other ones what is it, QQ plot and different things like that.
Absolutely, right. Seeing if they're normal. So what this is sort of a residual versus fitted plot. What we're looking at here is there a trend in how far off we are based on where our prediction is?
So the X's are
This is the predicted value. That's right.
Residuals, okay.
That's right. And so because of that, what this plot would tell us, sometimes if you have an increasing variance, you'll see a fan on this, right? Or decreasing, you see a different, like a trend. If you don't see a blob,
that's kind of almost not
That's it. You want to see a blob here. This is the blob plot.
Would you mind just like quickly going through the other plots?
I haven't thought about that in a long time, but I'll try. So we got residuals versus fitted. The normal QQ, this tells us whether the residuals follow a normal distribution, and some don't.
Okay.
This is the scale and location. This is fitted values by standardized residuals. This is also trying to tell us whether or not we have homogeneity.
So this is similar to the first one.
That's right.
It's more just the standardized.
That's right.
Okay.
And then leverage. This is going to tell us whether we have a point that might be overly influential. So leverage, Cook's distance is sort of another metric here, and these are leverage by standardized residuals. So this is telling us whether one of our observations is causing undue influence on the other parameters.
And I see there's dotted lines. It would fall like outside.
That's right. The Cook's distance is something that we define a metric to say where we would start to be concerned. So this is telling us none of our observations are unduly influential, potentially. By the way, there's Bayesian versions of all of these if we really wanted to get into it, but that's probably not in this class. So,
Thank you.
you're welcome. Bringing back memories. Sorry, I can't pass linear models anymore, at least not that deep. It'd take me a while. I'll get it back, though. I'll get it back. All right, what do I need to define? So I'm going to call gamma as my parameter for the variances. So let's start with the model first and work backwards. We're going to use our model matrix X, because I'm lazy. Remember the model matrix? It tells us groups, it tells us X, it tells us the intercept. I'm going to use it and multiply a parameter vector called gamma. So what does that mean? For each person's value of X, or group they're in, or interaction value, we're going to get a specific prediction for what their standard deviation, or residual standard deviation should be. Okay. So now I need a gamma vector X, or gamma. Gamma itself I'm going to follow with a multivariate normal distribution. It's going to function very much like gamma is the betas for the standard deviation, is really what that is. And then I need to take the exponent of that to keep it positive. So then I need to define the vector gamma, and I have to define its mean and covariance on input as well. So basically, everything I did to define the location or the mean side of this model is replicated on the variance side of this model with a different set of parameters. Remember, gamma contains different numbers than beta. So there's different coefficients. And the other difference is that we have to make that in inverse length function to keep it positive, to keep it in the range. Yes?
So are we going to have a gamma
For each
Predictor?
predictor, yes.
Okay.
Yes, that's right. And I did it this way because I'm lazy. I probably don't need one for every predictor, but I have X, I'm going to make it work for me. So,
This particular model is the full model.
Yeah.
With interactions, right?
That's right.
Thank you.
So for generated quantities, again, we may want posterior predictive checks. Here, the difference is, for our log likelihood, is we have to give it the mean and we have to give it the standard deviation for each person. So I'm just going to run through it. I'm running out of time, so I want to get to the end of the cliffhanger. Dun, 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 dun. Compiled. Now, Stan will actually start to complain a little bit when I run this because the first values it uses for variance are very close to 0, but then it quickly gets off of that. Now let's see if it converged. Let's think about it. Hey, that looks like convergence to me. What do you think? Let's take a look at our parameters.
Is that warning what you were just saying in terms of like the 0 thing?
This, yeah, that's something is going on. So what happens in the location, the scale model, you can get some really bad results as the closer you get to 0. The tolerance of numerical stability starts to go crazy. And that's what I think what's happening here. I'm not exactly sure, but I think that's the case. If we look at our gammas, they're right here. I'm not going to interpret them, but let's just see. The main thing we want to think about is this parameter, do we have a posterior interval that includes 0 in it? Because if it does, if it includes 0, we're going to say, yeah, it probably could be 0. But if it doesn't, that tells us, yeah, there's likely to be some type of trend in variance now, or trend in standard deviation based on that feature. And I'm just going to quickly make this simple and look at the Q5 and Q95. So gamma 1, that's our intercept of all of our gammas. and it is positive, the intercept is going to be positive. It just has to be, right? Here are other terms. This one has 0 in it. Wait a minute. Gamma 3, though, does not include 0. That is the group parameter, believe it or not. That's like group 2. So that tells us the difference in variance for group 1 versus group 2 is different. So they're not the same. Gamma 3 does not have 0 in it. Gamma 4, sorry. Gamma 3 and gamma 4 don't have 0. Again, those are our group-based parameters, not having 0 included in it. The other parameters have 0. So what we're gathering from this result, if we were just looked at this without model fit or model comparison, we would say it seems like the residual standard deviation, or how accurate our prediction is, varies by group in this analysis. That's what it's telling us. Or another way of putting it, homogeneity of variance doesn't hold. What's the implication of that, you think? Let's take a quick look here at,
I mean, if we let the variance vary,
yeah.
our predictions will be better.
So here is our posterior standard deviation of the betas when we didn't let the variance vary. So let's just go down 3.5, 4.3. Now it's 6.5, 1, 6.6. What's happening is our posterior, because the variance, the residual variance in our model, it implicates issues with our betas, our coefficients. It talks about how accurate they are. So now we have, because we've included uncertainty on the variances, we get less certainty about the model parameters. Anyway, so they're yoked together. But, big picture, let's go back to the main thing about today's lecture, which is the model comparison. You don't want to see that. Let's take a look at model comparison. Right down here. WAIC for model 6 with homogeneous variance, model 7 with heterogeneous variance. We compare the bottom number here. The lower is better. Heterogeneous variance is lower. How about leave one out? I'm just going to put that in the LOO compare. Turns out heterogeneous is on top. That means it's better. The difference in expected log posterior density was -17 with a standard error of 5. So if I'm looking at this from a model comparison point of view, I say not only do we have heterogeneous variance, but that model seems to fit better. So I'm going to use that model as my result. How about that? There's your model comparison that's meaningful. Got like 2 minutes left. Side eye still there? What is this guy doing? No?
I was gonna say I like it. My question is about the gammas in terms of like if some of them are significant, right?
Mm-hmm.
And some of them aren't.
Yep.
Do we always just model all of them? Do we just do do we let the ones that
I'm
very
I'm
like,
woefully underread in this area of linear models.
Okay.
So I don't know the answer to it. I don't know that this approach gets used very often. I also know that we put a linear model on gammas, and for things like variances, nonlinearity is probably pretty big. So
wait, what? Sorry.
Yeah.
Well, my brain turned off for a hot second.
Yeah, no problem.
Can you say what you said again?
yeah, the linear model, we put linear, so we're saying, like, for instance, gamma 2 is our coefficient of the variance multiplying x, which was a continuous predictor. That's basically saying that as x goes up, the log of our variance is decreasing linearly. But that's probably not a good assumption. There's probably some asymptote in variation based on the prediction of x and y. So there's probably some nonlinearity that's going on here. But the bigger feature is the two group-based coefficients right here are saying that. So I'm not up to speed on what happens here. I think generally speaking, people don't use this approach. They tend to just use a weighted least squares for the analysis, or they do something to their standard errors. But in a Bayesian sense, what I wanted to give you the sense of, because the cool thing about Bayesian to me is because you have to build all the parts of your model, now what we call assumptions or what we call whatever, you're starting to see this is a model choice. Not just because of Bayes, though. We could do the same thing with a likelihood function and do ML with this as well. So, yeah.
Can you update these files?
Update?
Yes, this one, because I was looking up, for example,
It's not online.
the server.
Oh, okay, I'll update it. Yeah, sorry.
We don't have this version.
I will put it there. I'm sorry. I really made it the cliffhanger. Suspenseful. All right, so I'm going to leave you to that. Think about that for next week while I'm gone. Enjoy your week off without me. And when we come back, it's all psychometrics the rest of the way. Thank you for being here. Have a great Friday, great weekend. And thank you to all online as well, too.